Welcome to today's lecture, in which we are going to see the role of contaminants, how they will affect the experimental aspects of nuclear astrophysics, even nuclear reactions in general as well. So, which are applicable even for the experiments or nuclear reactions relevant for astrophysics. In the previous class, I have discussed the considerations when backing materials are used and the target materials are used, and as part of the continuation of target materials, associated equipment. So, let us see one more parameter, that is contaminants, and after discussing the contaminants, I will throw some light on nuclear radiation detectors. What are the general aspects of the detectors and how many types of detectors are available and relevant for nuclear astrophysics related experiments, and how the spectroscopy of charged particles, neutrons and gamma rays can be studied using various types of nuclear radiation detectors. So, let me see how much I can cover in this lecture about the detectors. Remaining part I will continue in the next lecture. Okay, so coming back to the targets and associated equipment, it is contaminants. Many a times the presence of contaminants either in target material or in backing material, that means the support for the target material in the back side, not the supporting material for the holding the target material. So, in the backing material or in the target material, the presence of contaminants can hamper the studies of nuclear reactions. Okay. You can always say how the contaminants can disturb the data that we are looking for, because the concentration is very small in this backing materials and the target materials. Yes, the concentrations of these contaminants are very small, there is no doubt. However, depending on the incident beam type and energy, there is always a great possibility that the cross section of these contaminants with the incident beam could be very high. The probability for the reaction to happen between the incident beam and the contaminants could be very high. So, because of the high cross section, the emission of particles, maybe gamma rays, maybe alpha particles or some scattered particles or neutrons, they will always contribute to the original data that we try to collect from the detectors. So, we should ensure that contaminants are not hampering the nuclear reactions of our interest. Okay. Then how to eliminate the contribution of contaminants? First, you would run the experiment by taking the target material and the backing material. You see whatever count rate is there from the detectors, because it is a counts or count rate which helps us in getting the information of a yield of the nuclear reaction, and that yield is used to find out the cross section and then reaction rate, S factor and what not. So, take the data by considering first target and backing combination, and then you remove the target material, take the reaction only with the backing material and you take the difference. That will help us in getting rid of the contribution of contaminants present in the backing material. All right. So, this is how one can take care of the contribution of contaminants in the backing material. So, there are some other issues as well. For example, oxidation, especially when neutron induced reactions are considered, metal samples are when used, then oxidation is one of the problems, and sometimes it can change the composition of the target material. And because of the hygroscopic nature, that means absorption of the moisture from the air, the target material can develop change in the composition, and because of the change in the composition, what will happen? Of course, there is a change in the data that we are looking for. What are the famous or important contaminants in nuclear reactions? Let me show you a table. Okay. So, here is a table. One of the common contaminant is fluorine 19, and you know, proton induced reactions, they are very important for nuclear astrophysics. When they interact with F19, you will get alpha and gamma rays, and oxygen 16 as the product nucleus, which is stable. You see the energy of the gamma ray about 6.1 MeV. The target material, if causes a nuclear reaction in which the gamma rays of energy, say at 6 to 6.5, and then in that case this fluorine 19 also is giving rise to 6.1 MeV gamma ray. So, there is an overlap. So, you can see the emission of gamma rays of energy of 6.1 MeV can change the count rate if the nuclear reaction of our interest also emits gamma rays of energy around this 6.1 MeV. So, how to take care of this? There are methods to take care of the contribution of contaminants. The second contaminant, boron 11. When proton reacts with boron 11, you are getting gamma ray. Here the energy is 4.4 MeV, and it can also emit alpha particles of different energies, and proton with nitrogen 14 can give rise to gamma ray of energy 4.4. Proton sometimes by reacting with carbon 12, it can give you gamma rays same like 4.4 MeV, and then carbon 13, this is one of the important contaminants which can hamper the nuclear reaction of our interest. Here 2.3 MeV gamma is emitted. Now, this is one of the major contaminant C13, which is giving rise to reaction of alpha plus carbon 13 gives rise to oxygen 16 plus neutron, and these neutrons, carbon 13, when it reacts with alpha, that means the incident beam we are assuming as alpha, the reaction can lead to the emission of neutrons, and these neutrons poses problems when detector background is taken. So, these neutrons will certainly hamper the detector background. Second way, these neutrons by undergoing inelastic scattering with the surrounding material or absorption, anything can give rise to gamma ray, and these gamma rays can hamper the detector count rate. So, we do not want this gamma rays from carbon 13 which is giving rise to neutrons, and those neutrons by interacting with the surrounding materials, they are via absorption or inelastic scattering, they are giving the gamma rays to the detector, and it is polluting the data which we are expecting from the nuclear reaction of our interest. So, this is one of the important reaction in which contaminant can hamper the nuclear reaction. So, some more reactions are given here and corresponding gamma energies. All right. So, after discussion on contaminants, before that I have discussed target materials, backing materials. Now, it is the time to discuss the second important aspect of experimental nuclear astrophysics, and it is nuclear radiation detectors. So, detector, as name suggests, it detects and measures the nuclear radiation. How it works, how many types of detectors are available, and what kind of detectors are preferred for the nuclear reactions relevant for the astrophysics. You might have seen GM counters, scintillation detectors in your teaching laboratory. Of course, the knowledge that you might have gained by doing experiments with GM counters and scintillation detectors will surely help you in understanding the detectors aspect that I am going to discuss. All right. So, before the discussion on detector I can take up, I would like to spend some time on the radioactive sources and interaction of radiation with matter. Interaction of radiation with matter. Because before using the detectors for the nuclear reactions relevant for astrophysics, you need to test the detectors in the laboratory. You need to test and calibrate the nuclear radiation detector before using it for the nuclear reaction inside a particle accelerator. When particle beam incident, when particle beam falls on the target material, because of the nuclear reactions, when particles are emitted, detector is going to detect them. If they are charged particles, which are the products of the, the reaction products are charged particles, then one can always place the detectors inside the target chamber, because the travelling of charged particles from the target material, the location where the nuclear reaction is taking place, before reaching the detector, if the distance is large, they will get absorbed. So, generally the detectors for detecting the charged particles, like Hoyle state measurement, if we want to detect the alpha particles when reaction take place for the study of Hoyle state, then alpha particles are emitted immediately after the target materials or target material, and near to the target material you need to place the charged particle detector, and that whole environment has to be within the vacuum region. That is why we try to maintain about 10 to the power of 6, 10 to the power minus 6 torr, or if possible, if you have a better vacuum system, you can go for 10 to the power of minus 8, minus 9 torr also, so that the loss of charged particles is very less. All right. So, as I said, detectors have to be calibrated using radioactive sources in the laboratory, not particle accelerator beam hall, but in the laboratory you have to test the nuclear radiation detectors, whether it is performing well or not. To test the detectors, of course, one needs radioactive sources. So, what are the widely used radioactive sources to test the nuclear radiation detectors? Let us discuss one after the other. All right. Let me start with most widely used gamma source across the world, cesium 137. It is a monoenergetic gamma source. So, I will explain the decay scheme in detail of one or two sources. Remaining sources I expect you to study yourself through textbooks or material available in the internet. So, let me spend enough time on the decay scheme of a radioactive source, in this case a cesium 137, which is widely used to calibrate and test the nuclear radiation detector. Of course, this is a case when the nuclear reaction emits gamma rays, and by detecting the gamma rays we want to measure the cross section of the nuclear reaction. All right. See here. So, it is 30.17 years half life. All right, and the spin and parity is given by 7.2 plus. You know how to get this using the shell model, that I am not discussing here. So, because it is unstable, it will decay by beta minus, because neutron number is more, and 94.6% decays to the first excited state, of barium. You can see barium 56, the atomic number has increased by 1. So, 94.6% of the cesium nuclei decays to first excited state of the barium, and remaining 5.4% will decay directly to the ground state of the barium. In any case, it is a beta minus. Whenever you see the decay scheme of any radioactive source, especially if it is beta minus, then some energy value is always given in the decay scheme, and in this case 0.512 MeV is the end point energy of the beta rays, because you know, if you see the energy versus the intensity of beta rays, it basically is like, it is a continuous distribution, isn't it? It is a continuous distribution, and this is the end point energy E max, and here the 0.5120 is the maximum energy of the beta particle in this decay. Similarly, in this 5.4%, 1.174 is the maximum energy of the beta minus particle. So, if at all you can measure the energies of the beta particles using some method, then it is not only one energy, because the energy distribution is continuous in case of beta sources, right. Now, in 94.6%, only 90% of it will decay through the gamma rays, remaining goes to the internal conversion. All right. So, 90% of 94.6 gives rise to 85.1%. So, if you have 100 cesium nuclei, how to get it? The manufacturer in general gives the activity, normally in terms of microcurie or becquerel, and you know how to convert microcurie to becquerel, fine. So, if 100 cesium 137 nuclei undergoes decay, 85 gamma rays are emitted from the source in all directions if it is point isotropic source. So, in general, point radioactive sources are used in general. Sometimes we can always use Merendale beaker and extended sources kind of thing. So, I am using the simplistic version, that is point radioactive source, which emits gamma rays in all directions. All right. So, this is a decay scheme of cesium 137. Second, cobalt 60, it is a double gamma emitter. Okay, double gamma emitter. When I say this, what does it mean? Its half life is 5.27 years, and cobalt 60 mass number, because of the neutron rich, one neutron gets converted into proton, and 99.88% will reach to the second excited state of the nickel, and as part of the selection rules, it goes to the ground state via emission of 1.173 and 1.332 MeV gamma rays, and very small percent like 0.12% will decay to the first excited state of nickel. Nickel 60 first excited state and nickel 60 second excited state. All right. So, one nucleus is giving two gamma rays of two different energies. Of course, they are closely separated with each other. So, this is one of the source which can help us to test the ability of detector in terms of resolution, that we will discuss, I will discuss in due course. All right. Now, let me show you a source which decays through beta plus positron emitter. Okay. So, beta plus, you can see sodium 22, atomic number is 11. All right. And when positron reacts with the electron in the surroundings, it will give you two 511 keV gamma rays, and the reaction happens through both electron capture and also positron decay. So, you should know the meaning of electron capture, positron decay. You can go through any nuclear physics textbook, it will be explained very clearly. All right. So, via electron capture and positron decay, when sodium 22 undergoes decay, they reach to the first excited state of neon 22 via electron capture, via positron decay. In both manners, it reaches to the first excited state of the neon 22. Atomic number decreases by 1, because proton is basically getting converted into neutron plus positron plus neutrino. That reaction you know very well, right. So, we have 1.275 MeV gamma ray. In addition to that, the beta plus reacts with electron in the surroundings, it gives you two 511 keV gamma rays. So, little bit deviation from the discussion. Let me pose you a question. You have been given a source, for example, this is a radioactive source. Okay. Whether it is a positron emitter, that means beta plus or beta minus, what kind of decay is happening? How to know that? It is quite simple. If this radioactive source emits positrons, then from the detector you will get a signal corresponding to 511 keV always. So, in the response of the detector, if you find 511 keV, that means the radioactive source is decaying through beta plus, and if there is no 511 keV, it means the source is decaying through beta minus. So, that is how one can differentiate beta minus decay and beta plus decay through radioactive sources. Now, after discussing this gamma sources, let me show you one of the widely used neutron source in the laboratory. Why do we need a neutron source? Because as I discussed in S process, R process, the seed nuclei has to absorb the neutron and it gives rise to new element or new isotope, new nucleus is formed, but that neutron is emitted in some reaction. If you want to study that nuclear reaction in which neutron is emitted, then you need to use neutron detectors in the particle accelerator. So, as I said, before putting the detector in the particle accelerator, you have to keep in the laboratory and you have to test and you have to calibrate it, you have to see its performance. So, for that also you require one neutron source in the laboratory. So, for producing the neutrons, though there are nuclear reactions which can emit the neutrons, we have a few sources available in the available in the laboratories, using which one can test the performance of the detectors for neutrons. And one of the most widely used neutron sources across the world is fission source californium 252. Okay. So, this is a californium 252, 97% of californium 252, this is called as transition probability, decays via alpha process, okay, and remaining 3% decays via fission process. This is called as spontaneous fission. And you know, in the spontaneous fission, you will get fission fragments, you will get gamma rays, you will get neutrons. And these neutrons and gamma rays, they are not monoenergetic, they are distributed in terms of energy. So, you measure the neutrons of different energies using detectors which you want to use for nuclear reaction in the particle accelerator. Okay? And the energies of the neutron ranges from say 1 MeV, around 1 MeV to 15 MeV. Now, after this neutron, let me show one widely used alpha source, that is americium 241. In the laboratory, teaching laboratory in your department or in university or institute, if you have Rutherford alpha scattering experiment or alpha spectrometer, you can see it could be either plutonium or americium. So, normally the energies ranges from 5 to 7 MeV. Here in case of americium 241, the energies of the alpha particle, they are two different numbers you have, like it could be 5.486 MeV, it could be 5.443 MeV. Here one interesting point I would like to highlight. You see here 59 keV gamma ray. Why so special it is? You know, gamma rays are highly penetrating, their energies are higher than normal characteristic X-rays, right. So, this gamma rays energy less than 100 keV is not very easy to get. So, sometimes if you want to see the response of detectors for low energy gamma rays, go for americium 241. It emits 59 keV gamma ray. So, it is widely used for low energy measurement of the detector. And anyway, alpha rays will get absorbed in the air, do not maintain the vacuum between the detector and source. So, you have only gamma ray. So, you can get rid of alpha particles by maintaining some distance between source and detector, and gamma ray can easily pass through the air and falls on the detector. It gives you response for the 59 keV gamma ray. Alright. Okay, so these are the radioactive sources which are widely used for testing the detectors. Now, I have used a word, calibration of detector. So, let me take for the simple case gamma rays. How do you do it? You use 137 cesium and you use the 60 cobalt, it gives 1 energy, it gives 2 energies, and these 3 gamma rays will give some channel numbers in the electronics, okay, and you plot channel number on the x axis, energy of the gamma on y axis, and in general you will get some kind of a linear plot So, with this one can check the linearity of the detector. You can always ask, okay, we are calibrating the detector only up to 1.33 MeV, correct. If the gamma rays emitted in the nuclear reaction of our interest, the energy range is like 10 MeV, 15 MeV, 20 MeV, then one can go for nuclear reactions for calibrating the detector itself. But here I am discussing the calibration of detectors within the laboratory using radioactive sources. For high energy gamma rays, yes, there is one source, that is americium beryllium source, americium 241 beryllium 9 source, where americium emits alpha, reacts with beryllium, gives rise to neutrons and also gamma rays, and here the gamma ray energy is 4.4 MeV. So, you will get one mono energetic gamma ray from the americium beryllium. So, after 1.33 MeV by cobalt 60, you have to go for 4.4 MeV. In between these two numbers, it is difficult to get the radioactive sources which emits gamma rays in this range. All right. Okay. So, once you calibrate the detector, you place in the particle accelerator beam hall and detect the gamma rays emitted by the nuclear reactions. All right. So, let us continue. When the radiation is emitted from alpha source, beta source or neutron source or gamma source, they are detected and measured with the help of a detector, right. But how do they interact with matter? It could be liquid, gas or solid material. So, it is very important to understand the interaction of nuclear radiation with material. Accordingly, you can choose the material of your choice, and accordingly you can choose the separation between the target material and the detector within the particle accelerator beam hall. All right. So, if I consider the charged particles like alpha particles, protons, electrons or heavy ions, then the important topic is linear stopping power for charged particles, that is S energy loss per unit length, which is also called as specific energy loss, and standard Bethe-Bloch formula minus dA by dx is this pi is a constant charge, this is the incident particle Z and velocity of the particle and number density, and where this B is given as this atomic number of the matter with which radiation is interacting, and remaining terms are well known. So, using this one can find out the energy lost per unit length, and here you can see the specific energy loss in air MeV per centimeter with respect to particle energy. What kind of particles we have considered here? Alpha particles, protons, electrons. So, here for nuclear astrophysics we are mainly interested in the protons and alpha particles. So, one can get the information of this with the help of SRIM, that means stopping power and range in matter, or using different types of codes also one can find out the charging this specific energy loss. And when you see with respect to distance of penetration, we call this as a Bragg curve. Okay. And for single particle you can see how it looks like, and for parallel beam, because of a phenomenon called as straggling, you will get this kind of response. And if you plot specific energy loss with respect to energy for helium ions in copper, helium 3 ions in aluminum and alpha helium 4 in nitrogen, then how the specific energy loss looks like. So, you can see in this diagram. So, in the next lecture I will explain the interaction of gamma and neutron with matter. Thank you for your attention.